Levels of abstraction. A hardware model can be written at varied level of detail. Lesser the detail, greater is the level of abstraction. Depending on our need, we can choose any. VHDL provides different levels of abstraction. VHDL supports three main levels of abstraction. 1. The behavioral level. We can describe the system using mathematical equations, and there is no timing. The system simulates in zero time like a software program. It has neither a clock or delays. Algorithms are not synthesizable. 2. The register transfer level, RTL. Here, we partition the system into combinational and sequential logic, using constructs and coding styles supported by logic synthesis, and it has one or more explicit clock. You define timing in terms of cycles based upon one or more defined clocks. All operations are scheduled to occur in specific clock cycles. However, there are no delays below the cycle level. RTL is the input to the synthesis. 3. The structural level/gate level. You instantiate and interconnect predefined components from a technology library, which can include vendor-provided macro cells and logic primitives built into the language. There is also switch level, which is not supported by VHDL. Layout deals with silicon structures and polygons to create basic logic functions. EDA tools facilitate the translation between abstraction levels, as shown. It is important to understand that as we move to higher levels of abstraction, we are giving up details about our design to gain faster capture and simulation. So test benches and simulation models are written in behavioral level code for faster design entry and faster simulation. ASIC or FPGA designs must be entered in more detail, at RTL. This will take more time to enter and simulate, since it must include details of combinational/registered logic for the synthesis tool. The output of the synthesizer is further translated to layout for proper place and route by the EDA tools. Some areas of design may be entered at the logic level, example handcrafted asynchronous logic. Higher abstraction levels allow you to describe your design functionality without being concerned about the details of its implementation. Typically, a design is entered directly in RTL VHDL. The RTL must be functionally verified using a VHDL simulator. A test bench model is written to apply stimulus, extract results and verify results. Since the test bench will not be synthesized, there is no restriction in use of language constructs or modeling style. Hence, they are written in behavioral level VHDL. The design is read into a synthesis tool and the target technology for the design is specified. The design is then synthesized to a gate-level netlist. This can be verified using the original RTL test bench. Layout is then performed for ASIC designs, or place and route for FPGA-CPLD designs. Timing information can be extracted from the layout tools and back annotated into the netlist, to perform function and timing verification using a simulator. The flow described here is very simplified and many variations exist. If your company is already using HDLs, then they should have a design flow in place. Otherwise, if you are new to using HDLs, understanding and developing a design methodology is a very important first step in using HDLs.